Hello everyone, this is Fahim from Exam Essentials, and today our main objective is going to be to solve this paper from Chemistry Unit 4 Jan 2025 examination series. So without wasting any more time, let's just get started. Right. Which reducing reagent is used to convert carboxylic acid to alcohols, right? So suppose you have this carboxylic acid over here, carboxylic acid, right? And you're going to convert this into some sort of an alcohol, ROH, right? So this is going to be, suppose, our carboxylic acid to alcohol. So basically we know that oxidation of this alcohol to carboxylic acid needs up potassium dichromate 6 dilute sulfuric acid, right? But the reduction process, this is the reduction process, and the reduction process of converting this carboxylic acid to alcohol is carboxylic acid to alcohol requires of lithium LiAlH4 in dry ether. So oxidation requires of potassium dichromate 6 K2Cr2O7 along with dilute sulfuric acid, right? And the reduction is gonna require LiAlH4 in dry ether. So in most of the chemistry question, wherever you're encountering these reduction questions, you basically need to know this LiAlH4 in dry ether. So yeah, so D is gonna be the answer. So let's just move on to the next question. A polyester is made from pentane 1,5-diol and pentane dioic acid, right? What is the repeat unit for this polyester, right? So basically, just a basic idea, right? So pentane and pentane, right? Pentane means that there is gonna be 5 carbons, so C5. Here, pentane dioic acid means that again 5 carbons, C5. And dioic, this di means 2, right? So there should be 2 carboxylic acids, 2 COOH group, right? And diol means that there is these 2 alcohol groups. I mean, in exam you basically do not need to do all of this. You can just look at the options available and just select up an answer. But as I'm doing through the question papers, I do need to make sure that each of these steps are clear for most of you, right? Because not all of the students are going at the same pace. So yeah, I'm making up this video in a way so that it is helpful for the students who are struggling with all of this. Diol means 2 OH groups, right? So these alcohols and these carboxylic acids combines together in a condensation reaction to form a polyester, right? So let's just identify the one that have 5 carbon, 3. So this is 3, 4, 5. Okay, 5 carbon. We have 5 carbon here, and we also have 5 carbon over here as well. But the main issue is gonna be there should be a COOH, there should be a COOH as well over here. Okay, let's just take a look at closer look at this. COOH, H is lost from here, and COOH, H is lost from 3, 4, 5. Okay, 5 carbon. However, we have 5 carbon over here as well, and suppose there was this H and there initially was an H over here. So one more thing that I have to make sure is that in condensation reactions, these alcohols are going to lose its OH, and these carboxylic acids are going to lose their OH group, and the alcohols are going to lose their H groups, right? So this is the form pentane 1,5-diol. And let's just take a look at P. It seems that this one is okay, but I will just keep this as to be an answer. Let's just go on to the move on. 5 6 6 7 carbon. So this is clearly B is not the answer. And let's just see, so should be the answer, but let's just 5 6 7. So this is clearly not the answer, right? So 3 4 5 and 5, right? So either it is A or either it is C, right? So let's just take a deeper look into it, which should be the answer. So 3 3 3 4 5, okay, we have 3 4 5. Oh yeah, so basically the carboxylic acid should be losing up its OH, right? As I said, it should be losing up its OH, right? So there shouldn't be any O with this carboxylic acid, right? It should be losing up its OH, right? So this should be the answer. This should be the repeat unit. Clear? So the acid is gonna lose the OH and the alcohol is gonna lose the AH, right? So this O that you are seeing over here is the O from this alcohol side, right? Clear? All right, so let's just move on. Moving on to the next question. Question 3. When ammonia dissolves in water, an equilibrium results. The equation for this equilibrium is shown, right? So which of these acts as a Bronsted-Lowry acid base in this equilibrium, right? So first of all, I mean, from IGCSE and ACE chemistry, you should know that ammonia is a weak base. Weak base. As it is a base, it is going to accept a proton from this water, right? So water is acting as an acid. Now this NH4 plus can donate up its extra proton to become NH3, right? And right, NH3, right? So as it can donate up a proton, now it is acting as an acid. And this OH minus can accept up a hydrogen ion that was formed from this NH4 plus to form H2O, right? And as it is accepting up a proton, this OH minus is acting as a base, right? So basically I have written down this over here, and now it says that which of these acts as a Bronsted-Lowry acid and base. So the answer should be D, because NH4 is acting as the acid, NH4 is acting as the acid over there, and H2O is also acting as the acid. So answer D should be the correct answer. It said that Bronsted-Lowry acid in equilibrium, right? So let's just move on to the next question. A strong monoprotic acid, which means that it can donate up one hydrogen. Diprotic means two hydrogen, right? Hydrogen ions, right? So of concentration of this has a pH of this. What is the decrease in pH? So first of all, whenever you hear a term that has this strong in it, strong acid, the concentration of this acid, the concentration of this strong acid is going to be equals to pH. So pH is going to be equals to the concentration, that is 0.0100. You know that pH is going to be minus log base 10 to the power this 0.0100, right? Concentration of H plus. As I said, the concentration of H plus for a strong acid is gonna be the pH for a strong acid, the H plus, or let me just rephrase it, the H plus for a strong acid is gonna be equals to the concentration of it, right? The concentration is gonna be equals to H plus. So from here I plug in the value of this H plus, that is 0.0100, which is the concentration, and from here I do receive a pH, right? I do receive a pH. Then in the question it says that the initial pH is 2, right? So pH minus the answer that we find is gonna be the decrease in pH. So this is basically what I have done over here, and the decrease is B, 0.04. Clear? So let's just move on to the next question. Right. One of the stages in the manufacture of sulfuric acid involves the oxidation of sulfur dioxide to sulfur trioxide, equation 1. Okay. Equation 2, sulfur dioxide plus half oxygen leads to the formation of sulfur 3, okay, sulfur trioxide. The Kp at 25 degrees Celsius for equation 1 is this Kp, okay. What is the numerical value of Kp for equation 2, right? So first of all, Kp is what, right? Kp should be equivalent to partial pressure of products by partial pressure of reactants, right? So this is what I have written over here, and this should correspond to the first Kp of the first equation, and this should correspond to the Kp of the second equation, right? Now we can clearly see one thing, that is, if we multiply the power of this second Kp equation with 2, we can get the original equation. See, so if we multiply the power with 2, we should get something like this: P partial pressure of SO3 to the power 2 by partial pressure of SO2 to the power 2 times partial pressure of um, pressure of O2 to the power 1. See, this one, this equation and this equation matches, right? Since these two equation matches, I could easily say that Kp of the first equation is gonna be equals to Kp to the power 2 of the second equation, because that is how we are making the first equation, that is how we are turning the second equation into the first equation. So what we're basically doing is we're multiplying this with the power of 2, right? So when you are multiplying this with the power of 2, we are converting it into the first equation, and we can then put the value of the first Kp, that is 4 into 10 to the power minus 24, into this equation, and from there we can easily find the value of Kp for the second equation, right? All right, so let's just move on. If you're unsure about any of these steps that I'm doing at this point, feel free to comment below. I will be more than glad to respond to you all, right? So yeah, let's just move on to the next question. The relationship between Kp and Kc. Okay, K is for partial pressure. Guys, give me a moment. Alright, so Kp is for partial pressure and Kc is an equilibrium constant, right? So the relationship between this is given below, where Kc is the equilibrium constant, this is the partial pressure, this should be gas constant, and the value given over here is 0.832 at atm per mole per Kelvin, and N is the number of moles of product minus reactants, okay? Moles of product minus reactant. What is the value of Kc at 25 degrees Celsius using the first equation, right? So here we have given 25 degrees Celsius, 25 degrees Celsius. So basically you have to convert this value into Kelvin, right? So how do you convert anything that is in degrees Celsius to Kelvin, right? So basically use this formula: temperature in Kelvin equals to Tc plus 273, right? And you can convert into Kelvin and degree Celsius using this formula. So this is a really handy formula. So I mean, note this down into your note copy or somewhere and store it, because you're going to need this for both your chemistry and physics, right? So this is how we convert it. So here we have the temperature in Kelvin, right? And the gas constant R is given over here, and we know that the partial pressure Kp equation for Kp value for the first equation is this, and we just need to find the moles, right? So N is the number of moles of product minus reactant, so 2 minus this one and this one, right? 3. So let me just take a look. N of product minus mole of reactant, right? So this is gonna be 2 minus 3, that should be minus 1, which is the value of N, right? So once you plug it into this equation, you're gonna get a value. So yeah, the value should be D, right? So let's just move on to the next question. Which equation represents standard enthalpy change of atomization? Okay, right? So first of all, before doing up these questions, give me a moment, guys. Right, so enthalpy change of atomization, right? So before doing up this question, you basically need to know what does the enthalpy of atomization means, right? So it is basically the process by which you form 1 mole of gaseous atoms, 1 mole of gaseous atoms from its elements in standard states under standard conditions, under standard conditions. So this definition is extremely helpful, right? So from here I could see that the standard state of iodine is solid, right? And we are converting this into 1 mole of gaseous atom, right? So this should be the enthalpy of atomization. Make sure that you know this definition, right? Because this definition is going to be handy when you are trying to deal with this kind of questions. Right, so moving on to the next question. The equation represents the second electron affinity of oxygen, right? Which equation, right? So electron affinity means that gain of electron, right? It is basically the reverse of ionization energy. So it means that of gain of electrons. So gain of electrons, second electron affinity, right? So it should be something like this is the first electron affinity, right? And it gains up one electron to form O2 minus. So this equation should be for the second electron affinity, right? And the second electron affinity is always going to be negative. This is because this oxygen already had a negative charge, right? And this electron also has a negative charge, right? And the negative charge is gonna repel each other, right? So to overcome this repulsion you need to provide up energy, right? And for this reason second electron affinity is always going to be exothermic, endothermic, endothermic. Endothermic. So the answer should be A. Let's just move on to the next question. Which compound has the greatest covalent character, right? Which compound has the greatest covalent character? So from here I could see that calcium, magnesium. Okay, so one thing that is common between these ions is that they all have a charge of +2, right? So now even though all of this has a charge of +2, I'm gonna eliminate this and this because they have a greater radius. This two has a greater radius, right? And the force of, let me just tell you one thing, the force of this, the polarizing power of a cation depends on charge density and radius, right? Radius. So I could eliminate these two because magnesium is smaller. So because magnesium is smaller than calcium, because magnesium is way down the group. Now between bromine and iodine, the radius of iodine is greater, right? Which means that first of all assume that this is the magnesium ion, right? And this is the iodine. So what this magnesium is going to do to this iodine is that it is going to distort the electron cloud of this iodine, because iodine is larger, right? And as it is a larger ion, it is easier to distort the electron clouds of iodine when compared with magnesium, and hence this magnesium iodide is going to have the greatest covalent characteristic, right? So let me just write this down because this is going to be handy. Force is going to depend on charge density, and the second factor is going to be the radius. You can note this down because this is an important concept that is going to be tested again and again, right? So let's just move on to the next question. Which pair of values will always give a thermodynamically feasible reaction? So whenever the reaction is feasible, del S total should be greater than 0. Del S total should be greater than 0, right? Now there is a separate chart for this, but basically I'm not a fan of memorization. So what I like to do is I like to try to figure out these questions, right? So del S total should be equals to del S total greater than 0, then the reaction is going to be feasible, right? So del S total should always be positive, right? Del S total is entropy of system is sys plus is SAR. Okay, now for one thing for SAR is that surrounding is minus del H by T, right? So when this is negative, system is negative, and this is positive, this is always gonna be this may be feasible or may not be feasible, because when this is positive and negative, would always give you a negative value. Now if the entropy of system is not large enough than this negative value, then del S total is gonna be less than 0 or negative, right? So basically for this thing, del S total to be always feasible, this thing should always be plus, right? And this thing delta H should always be negative, right? Because negative and negative is going to cancel out to become positive, right? And once it is positive, del S total should always be greater than 0 and or positive, right? So yeah, the answer should be D, positive and negative, right? So basically I have written this down over here, so you can take a look at this. So whenever you encounter questions like this, I would highly suggest you to write up this formula and basically deduce from this formula. So for reactions to be feasible, the del H total should always be positive or greater than 0, right? So let's just move on to the next question. Right, so this question is about the effects of changes on a system at equilibrium, right? The equation for the reaction between hydrogen and iodide is shown, right? So what effect, if any, an increase in pressure should have on the appearance of this equilibrium mixture, right? So whenever you increase the pressure, equilibrium shifts to the direction with fewer moles of gas, right? But the thing is, there are equal number of moles of gas on the left hand side and the right hand side of the equation, right? So we cannot answer with this, but however, as the pressure increases, the volume is gonna decrease, right? Because pressure is inversely proportional to 1 by volume, right? And as the volume decreases, I2 gas has a color, right? Iodine has a color, right? So the color of the iodine intensifies, so the mixture becomes more purple. Clear on this? So yeah, color increases, right? So let's just move on to the next question. He said that the equation for the manufacture of ammonia by Haber process is shown. All right, which changes would result in the increase in value of Kp, right? So Kp, K partial pressure, is gonna be equals to partial pressure of products by partial pressure of reactants, right? So the equation or the expression for partial pressure is gonna be Kp equals to partial pressure of products by partial pressure of reactants. Now it says that which change if any will result in an increase in the value of Kp, right? So what would cause the value of Kp to increase? So let's just take a look. An increase in pressure only. If the pressure increases, equilibrium shifts to the direction that has fewer moles of gas, right? So as the amount of product increases, Kp increases as well, right? This seems to be correct, but let's just take a look on some other options. Wait, an increase in pressure only, right? So as pressure increases, equilibrium shifts to the direction that has fewer moles of gas. Increase in the value of, okay, let's just take a look at the other options. A decrease in temperature only. So as the temperature decreases, equilibrium shifts to the right, right? Equilibrium shifts to the right, which means that the amount of product increases. So hence Kp is going to increase as well, okay? A decrease in pressure and an increase in temperature. Note, if temperature increases, equilibrium will shift to the right, because forward is exo, so backward should be endo. No change in pressure, okay? Answer should be either from A or B, right? Let me just take a look at it. Which change, if any, will result in an increase in the value of Kp? An increase in pressure only. As pressure increases, equilibrium shifts to the direction that has fewer moles of gas. And honestly, A should also be okay as well, but why have I selected B? Give me a moment. Oh, I forgot. So equilibrium constants, you just have to know thing. Pressure does not affect the equilibrium constant, right? Only temperature does. Equilibrium constants are affected by temperature. Hence, I have selected the one that goes with temperature, right? Because pressure does not change up equilibrium constant, so B should be the answer. So let's just move on. The equation for equilibrium between nitrogen dioxide and nitrogen tetraoxide, dinitrogen tetraoxide is shown. A change in condition results in Kp increasing from this to this, right? So Kp should increase when the amount of product should increase. If the amount of product increases, Kp should increase as well. Or if the amount of reactant decreases, then also Kp should increase, because Kp is directly proportional to the partial pressure of products and inversely proportional to partial pressure of reactants, right? So the equilibrium position. Oh, you do not basically need to know about all of this here, but let's read the question once more. A change in condition results in Kp increasing from this to this. Kp increases. What can be deduced about change in position of the equilibrium? So equilibrium should shift to the right, right? Because when equilibrium shifts to the right, the number of or the amount of product increases, and as the amount of product increases, Kp should increase as well. So answer should be A. The equilibrium position shifted to the product or to the right hand side. Let's just move on to the next question. What is the pH of solution of sodium hydroxide? So whenever it says something about bases or anything, so pH is gonna be equals to or whenever it says something about base, pKw is gonna be equals to pH plus pOH. So this is gonna be the ionic product of water pKw. So this is given as 14.53, right? So minus pOH. pOH is going to be minus log base 10 to the power OH minus 0.100 is going to be equals to pH. So this is what I've done over here, and I get a pH value of 13.53. So let's just move on to the next question. The pH of a dilute solution of weak carboxylic acid can be calculated from a K value. Which assumption is not relevant, right? So this acid undergoes partial ionization. H plus, concentration of H plus is going to be equals to A minus. So these are the two assumptions that you know. The ionization of water is, it says not relevant, right? Ionization is insignificant. Initial equilibrium concentration, this is also correct. Concentration of protons and carboxylic ions are the same, H plus and A minus, as I said over there. However, so we have eliminated these three, right? So the last thing should be our answer. So D should be our answer in short. The dissociation of carboxylic acid is complete. No, it isn't. The concentration of H plus should always be low when it says about the dissociation of weak acids. So this question is about buffers. The Henderson-Hasselbalch equation can be used to determine the pH of a buffer solution. This equation is shown over here. What is the pH of a buffer solution containing? This is the concentration of acid. This is the concentration of salt, sodium ethanoate. This is K, and this is the temperature. So what you have to do is you have to plug all of these values into these equations, and hence you're going to find the pH. So this is what I've done over here. See, that's 5.07. Now, what is the best reason for the use of buffers in foods, right? To improve taste? No. To help digestion of the food? No. To prevent deterioration of fungal activity, right? Because okay, so basically the fungal activity is going to release up acidic digestive enzyme to digest on the food, right? So whenever there is a buffer, it would prevent the acids from destroying the food. Moving on to the next question. The carbonic acid hydrogen carbonate ion buffer system in the blood involves the equilibrium as shown. Okay, how is the pH of the blood affected? Affected by exercise, right? So when you're carrying out exercise, you're carrying out aerobic respiration, right? Biology students, please. So when you're carrying out aerobic respirations, you're going to produce up carbon dioxide, right? So the concentration of carbon dioxide increases. As the concentration of carbon dioxide increases, equilibrium will shift to the right, and carbonic acid is produced. Carbonic acid dissociates to form H plus and HCO3 minus, and as H plus forms, the pH is going to decrease, right? So yeah, this is what I've written over here. The pH would decrease due to the equilibrium shifting to the right. Which has the greatest molar enthalpy, right? So solid, enthalpy of solid is less than liquid, which is less than gas, which means that gas has the highest entropy of everything, right? So this should be gas, this should be the two. However, the one that has more nucleons or higher molar mass would be more disordered. So from here, D is gonna be more disordered. So the entropy of D is gonna be the greatest. You basically have to remember this. This is a common question that generally appears. 15, and we'll be done with this. 15. A graph of concentration of Q during decomposition is shown. Okay, what is the half-life of this decomposition? So I have selected 9 to be my initial, and half of 9 is 4.5, so it should be something around here. So as you can see, drop the line, this should give you around let me find the number that is each box represents. So the way you do this is divide 30 by number of each box, that is 5 over here. 30 divided by 5, so each box should represent 6. So this should be around 120 plus 12, 120 plus 6 plus 6 equals to 132, and 132 is going to be the half-life. See, 132 minute is indeed the half-life of this equation. So yeah, let's just move on. Moving on, everyone. Moving on to the next question. All right, so this question is about pentan 2-one. Okay, it is a ketone. Explain why pentan 2-one has a lower melting point than pentan 2-all, right? So this is an alcohol, OH, right? And this is an ketone, COO, right? Now the melting temperature of pentan 2-all would be higher because pentan 2-one could form hydrogen bonds, and more amount of energy is needed to break these hydrogen bonds, and hydrogen bonds are the strongest intermolecular forces, right? So hence the boiling temperature of pentan 2-one should be greater, right? So a hydrogen bond is formed when an hydrogen is joined to FON, the three most electronegative elements, fluorine, oxygen, nitrogen, and the opposite and the adjacent molecule has an FON dipole, right? So there is this force of attraction formed between this, and this is what we refer to as hydrogen bonds. AS chemistry stuffs. So let's just move. This is what I have written over here. Pentan 2-all can form hydrogen bonds within its molecules, unlike pentan 2-all can form hydrogen bonds within its molecules. Unlike pentan 2-one, hydrogen bonds are the most strongest intermolecular forces and requires more energy to be broken down, right? Give a chemical test that distinguishes between pentan 2-on and pentan 3-on, right? So pentan 2-on and pentan 3-on include a substance, right? So for pentan 2-on, COO is next to a CH3, right? So for pentan 2-on, COO is next to a CH3, but for pentan 3-on, COO is next to a CH2, which in turn is next to a CH3, right? So if you do a iodoform test of this pentan 2-on, it is gonna give a yellow precipitate, right? Because these three hydrogens are gonna be replaced by iodines, right? These three hydrogens are gonna be replaced by iodines, right? The 3 hydrogens are going to be replaced by iodine, a yellow precipitate form that has an antiseptic smell. So yeah, you're going to form an iodoform. So basically I've drawn up the skeletal formula, but you basically do not need to draw. You can just draw the normal formula, but I would highly suggest you to practice drawing up these structures with these skeletal formulas. So iodoform test, this will lead to the formation of yellow precipitate with antiseptic smell, that is CHI3, right? And with pentan 2 on, yellow precipitate would form. With pentan 3 on, no precipitate will be formed, right? Give a different chemical test that distinguishes between pentan 2 on and pentanal, right? So for aldehyde we can add filling solution, and filling solution is going to turn red, a red precipitate form. And with pentan 2 on, with ketones, there isn't going to be any changes, right? This is an ketone and this is an alcohol, right? So let's just move on to the next question. Pentan 2 on and pentan 3 on and pentan 2 on, pentan 3 on and pentanal reacts in a similar way with one test, right? With one test. Identify the reagent and describe how the solid produced could be used to distinguish the original compounds, right? So whenever you are having a carbonene compound, a common test for this carbonene compound is gonna be with 2,4-DNPH. 2,4-DNPH, and this is gonna give an orange precipitate, right? And what you could do is you're gonna get 3 orange precipitates, right? So what you're gonna do is you're gonna determine the melting temperature using a thail tube or an apparatus containing oil, right? Oil bath. Or I forgot the name of this, but something oil bath, right? So here's this thermometer, and here's a tube where you have the sample whose melting point you want to determine, right? And then you compare the melting point with the database, right? And find out which compound it is. Right, so I have written that over here, that is with 2,4-DNPH, all of the compounds forms a brightly orange precipitate. Recrystallize the precipitate form, find the melting point of each of the precipitate using a thail tube, and compare with the database. You basically do not need to mention thail tube, but yeah, I have done that. I mean, you basically do not need to go in details of that. I will cover separate videos on thail tube and how to determine melting temperature in my unit 6 videos, right? So let's just move on. Pentan 2 on, pentan 2 on and pentan 3 on can both react with cyanide ions, right? Cyanide ions in the presence of a catalyst KCN. With pentan 2 on, a racemic mixture is formed, right? But with pentan 3 on, there is only one product, okay? Explain the differences, right? So with pentan 2 on, with pentan 2 on, a racemic mixture is formed, right? So this was pentan 2 on. Pentan 2 on. Let me just draw the mechanism for a bit quick. Oh, I have it drawn over here. So this is pentan 2 on, right? So the cyanide ions so the cyanide ion can attack from both above and below equally, right? And this leads to the formation of a racemic mixture, right? But with pentan 3 on, the cyanide ion only attacks from one direction. And one more thing, that is we have a chiral carbon center over here because we have 4 different groups, and as we have chiral carbon center, it would lead to the formation of a racemic mixture, as Cn minus could attack from both above or below, right? But with pentan 3 on, we do not have a chiral center, hence it would attack from the opposite direction of this OH over here, and as a result it would lead to the formation of one product only, right? Clear? So whenever you have a chiral center, you're gonna have a racemic mixture. So pentan 3 on is a planar molecule around carbon in COO. As a result, the cyanide ions, the nucleophile, can attack from both above and below equally. As a result, racemic mixture forms that shows no optical activity. Pentan 2 on has a chiral center, as there are 4 different groups around carbon onto which the cyanide ion attacks, right? Pentan 3 does not have a chiral center, and it does not have as it does not have four different groups around C onto which cyanide attacks. Hence, it is not an optical isomer, right? Clear? So, yeah. Yeah, let me just see if it is written. Yeah, this is the thing, right? So, yeah, let's just move on to the next question. Questions.
Let me guess. You are watching videos, taking notes, maybe even grinding late at night. But the marks, they are just not going up. You are stuck, and it's frustrating. But here is the truth, it's not your fault, it's the method. And that's exactly where Exam Essentials makes the difference. We at Exam Essentials actually offer two very powerful cores to navigate you towards success. The first one is the most popular high impact crash course. If you are just 4 to 6 months away from your exam, this course is going to be a lifesaver for you. The high impact crash course for the October 2025 and the January 2026 is already available. And the second course that we at Exam Essentials actually offer is the complete 1 year course. This is basically for the students who want full support from day one to exam day. And the best part, our students' results speak for themselves. Both the courses are actually open ahead of every exam session. No matter whether you are going to give your exam for the May 26, Jan 27, May 25, or October 25, doesn't matter. We always offer these two courses before every upcoming exam session. To join or know more, just check the description box below. You will find our WhatsApp number and Facebook page link right there. Let's turn your effort into results together.
So, question number 17. Esters are difficult to distinguish from each other using other chemical tests, right? So, NMR spectroscopy is often used. There are four ester isomers with the molecular formula of C4H8O2, and their displayed formula are shown. Okay, so this is ester P, ester Q, ester R, and then ester S. Okay. Explain which of these four esters can be distinguished from other three types by the number of peaks in the carbon-13 NMR spectra. Justify with, okay, so it said that there are these four esters, and which of these esters could be distinguished from the other three using the carbon-13 NMR spectra. So let's just start with ester P. Ester P, so this is gonna have one environment, two environment, three or four environments over here. This thing is gonna have the four environments as because ester P and ester Q are almost the same. So see, one, two, three, four. So they both are gonna have four environments, and hence we cannot identify between ester P and Q because they will be giving peaks at the same chemical shift, right, or ppm. So for ester R, you're gonna have one peak for this, two, three, four. We are gonna have four peaks over here as well. And for this one we're gonna have one peak over here, one peak over here, and this one is gonna have the same peak because these two methyl groups is joined to a carbon with a hydrogen that is joined to a oxygen, right? So this environment and this environment is gonna be the same. These two environments are gonna be the same. This is because these two methyl groups are joined to the carbon, to the same carbon, to the common carbon that is in joined with an oxygen of the ester thing, right? So yeah, so we can identify ester is because this is gonna have three peaks, whereas other esters are gonna have four peaks, right? So let's just move on. Explain, right? Ester is, this is because it will be having three peaks as there are three different carbon environment, right? And with other esters there will be four peaks as there are four different carbon environments. Okay, There are 9 esters with the molecular formula of C5H10O2, right? The displete formula of these two esters are given below. Okay, ester W and ester X, they have this displete formula. Ester W and ester X both have one peak with relative area of 3 in their low reservation proton NMR. Okay, they have one peak, singlet, right? Singlet is due to these 3 carbon atoms, right? Because in the adjacent carbon there is no hydrogen, and there is proton. Yes, because in the adjacent carbon there is no hydrogen environment, right? So this is going to be a singlet over here, and same thing is going to be for this as well, because in the adjacent carbon atom we do not have no hydrogen, so this is going to be a singlet or a single peak. So explain how these peaks can be distinguished, how these peaks can be used to distinguish these two esters, right? So first thing is that for ester W, this proton environment is joined to an oxygen that is joined to a carbon that is joined to an oxygen that is joined to a carbon with CO, right? So this, and check this one, this hydrogen is joined to a carbon that is joined to a carbon adjacent carbon that is joined to an oxygen with double bond, right? So here it is joined to an, this carbon is joined with an oxygen directly, and here this carbon, this proton is joined to a carbon, which in turn is joined to another carbon, which is in turn is then joined to oxygen with a double bond, right? So that is going to be the difference between these two. Ester W is going to have a peak in the chemical shift of approximately 2.8 to 4.3 pm due to HCNO. You can get this chemical shift for using your data booklet, right? All right. And ester X is going to have a peak in the chemical shift of 1.7 to 2 pm due to H, which is bonded to C, which is bonded to another C, which is bonded to an O with a double bond. Okay. You can easily get these values from your data booklet. Moving on to the next question. The displayed formula of two different esters are shown in the boxes. Two different esters. Okay. Label the displayed formula of two esters Y and Z to show the proton environment and the splitting pattern of each of the peaks in high resolution proton NMR spectra. Clearly indicate any equivalent proton environments. Okay, for any multiplet you may refer to the number as separate peaks in the multiplet rather than giving a name. Okay, I mean like pentate, sextate and so on, you can refer to that as multiplet, but I will be using the name, right? So first of all, this is identify of the patterns, right? So hydrogen joined to a carbon that has no hydrogen on it, right? So this is gonna be a single peak or a singlet. Okay, done with that. This is gonna be an hydrogen joined with a carbon that is joined with a carbon that has one hydrogen on it, right? So the splitting pattern is gonna be n plus 1. So we have 1 plus 1 number of hydrogen on the adjacent. So this is gonna be a doublet, right? This is gonna be a doublet. So splitting pattern for this is gonna be splitting pattern for this is gonna be hydrogen that is joined to a carbon that is joined to a carbon with one hydrogen over here, and hydrogen again joined with a carbon that is joined with a carbon with 3 hydrogen over here. So we have a total of 1 plus 3, so 4 plus 1 is gonna be equals to 5. So this is gonna be a quintet, right? This environment is gonna be a quintet, or a pentet works as well. So this is what I've written. This is gonna be a quintet. So this carbon, they have marked on this one. You can also circle this one and say this is gonna be a quintet, right? It basically is gonna be the same thing. And for the last one, let's just check over here. We have one hydrogen. By one hydrogen I mean that all of these 3 are hydrogen, because all of these 3 hydrogen are in the identical proton environment, right? So I'm just assuming to be, as I'm just taking one of this. So hydrogen joined with a carbon that is joined with a carbon that is joined with 2 other hydrogen, right? So this hydrogen is joined to a carbon that is joined to another carbon with 2 hydrogen. So on the adjacent carbon we have two hydrogen, right? So n plus 1 rule, 2 plus 1 is going to be 3. So this is going to be a triplet. See, this is going to be a triplet. Moving on to the next question is turning. Right, so again this thing is gonna be a singlet because there is no proton on the adjacent carbon atom. And for this one, this sorry, and for this green carbon, is joined to a carbon that is joined to another carbon with one hydrogen, right? With one hydrogen. We are not going to take this into account because these hydrogens are on a different carbon environment, right? So this is going to be a doublet. So taking the hydrogen of this environment, so one hydrogen joined to a carbon that has two carbons on it, all right, and the same thing is joined to a carbon that has one carbon on it, so 2 and 1 3, and same thing, hydrogen joined to a carbon joined to another carbon that has three hydrogen on it, right? So 3 4 5 6 6 6 and 6 plus 1, that is gonna be a uh, nonate. That is gonna be a nonate because we're assuming this one, right? So we're taking this one, so there is gonna be 2 2 to 4 2 to 4 5 6 7 7 plus 1 is gonna be nonate 8, right? So let's just move on. I believe there was a color with this thing. Okay, that one was supposed to be a red color because they both A are in the same environment, right? That is gonna be a nonate because 7 plus 1 8. And over here we have hydrogen, right? Hydrogen joined to a carbon that is joined to a carbon with one hydrogen on it. So this is gonna be a doublet, right? So when we're dealing with this, we have to just look on the number of protons on the adjacent. So from this carbon is joined to this carbon, which is joined to this carbon, right? Hence it is going to be a doublet because we have one other proton in the bind joined with the adjacent carbon, right? We are not gonna consider this carbon as well, right? We are just gonna consider the carbon that is next to it to find the splitting pattern, right? So all right, let's just move on. Draw the split formula of a ester with the formula C5H10O2, which only has two peaks, right? Which only has two peaks means that there is two environment, two proton environment. So the structure that has two proton environment is gonna be this thing, right? Whenever you see that you have two proton environments, so first thing is that you're gonna make up something that has a cyclical structure, right? So this COO and H, right? So this has two proton environments, right? How? Because this thing and this thing gonna have the same proton environment, right? This thing and this thing is gonna have the same proton environment. Sorry, and there is gonna be another carbon over here. See, okay, right? So all of these three has the same proton environment, right? And this one has a different proton environment. So in total, there are gonna be two peaks as there are two different proton environments, right? So whenever you see that there are two or single, you're gonna you're gonna create up a cyclical structure, because when you create up a cyclical structure, see, this carbon is joined to this carbon, this carbon is joined to this carbon, this carbon is also joined to this carbon, and this carbon is joined to something, right? So all of this would give a single peak, right? Hence we try whenever uh, there is a question about two or three environment, what we try to do is whenever there is a question about two or three environments, so what we try to do is we try to make up a cyclical structure, right? So let's just move on. I can see one of you asking that why there is no peak for this, why there is no peak for this carbon, right? Because this carbon, does it have any hydrogen attached to it? No, right? It doesn't. So hence it wouldn't show any peak, right? So then moving on to the next question. This question is about reaction kinetics. Halogen alkenes are hydrolyzed by aqueous alkali to form alcohols. Okay. Um, alcohols. Nucleophilic substitution reaction is then the rate equation for this reaction with halogen alkanes is shown 1 bromobutane. This is a primary halogen alkane, and primary halogen alkanes undergo SN2 mechanism. What does 2 represent? 2 represents the number of molecules or ions that are involved in the rate determining step. And what basically is this rate determining step? It is the slow step of the reaction, slow step, right? And yeah, primary halogen alkane, first degree halogen alkane undergo SN2 mechanism, because if they underwent SN1, then a primary carbocation would be formed that would be less stable, right? And 2 bromo 2 methyl propane, this is a tertiary, and it undergoes SN1 mechanism. I could just clearly see from the equation either it is undergoing SN1 or SN2, because here I can get a clear indication of either it is going to be 2 molecules involved in the rate determining state, or there is this 1 molecule, right? So yeah, let's just move on. Explain how this rate equation can be used to deduce different reaction mechanisms of the reaction of hydroxide and with this halogenoalkanes. Okay, so this is basically the mechanism. So for this primary halogen this is going to be the slow step of this reaction, and this is the transition state. And yeah, as the reaction progresses, you are left with the your product, desired product, right? And with secondary halogen first of all the bromine is going to get separated, and this is going to be the slow step, and then this OH minus is going to join, and the other step is the fast step, right? So basically if you show up these structures, then you basically do not need to write much of it, right? And for this 6 marker question, whenever there's a diagram that is needed, I went for just drawing up this instead of writing much of it, right? So yeah, this is what I have basically written down. From rate equation of 1 bromobutane, the overall order is 2, which means that 2 molecules are involved in the rate determining step. Hence it undergoes SN2 mechanism. And also this is a single step reaction because there aren't multiple steps, whereas for 2 bromo 2 methyl butane there are 2 steps. One is fast step and one is slow step, right? So that is a 2-step reaction. And from rate equation of 2 bromo 2 methyl propane, the overall order is 1, which means that 1 molecule is involved in the rate determining step, and hence it undergoes SN1 mechanism. This leads to the formation of tertiary carbocation intermediate that is less stable due to the electron donating effect from the alkyl or methyl groups, right? Alright, so let's just move on to the next question. An initial rates method may be used to investigate the kinetics of the reaction between hydrogen peroxide and iodide ions in acid solution. Okay. The equation for the reaction is given below. Hydrogen peroxide, this to converting to that, and water. Okay. The reaction mixture contains a small amount of thiosulfate ions, which reduces the iodine back to iodide ions. Okay, so thiosulfate is reducing iodine back to iodide ions. Okay. Okay, right. So basically, this question is from iodine clock reaction. So what basically you're trying to do is, first of all, as this reaction is taking place, right? As the reaction is taking place, you're producing up iodines, right? Then what you're doing it, you're using this thiosulfate to convert this iodine back into iodide, right? And once you do this, and thiosulfate is in limiting over here, and once all of the thiosulfate gets used up, surplus amount of ion that remains in the solution reacts with starch to form a blue-black color. You record the time for the blue-black color to appear, and basically you can use the formula rate equals to 1 by the time taken to produce the certain amount of starch, certain amount of iodine to turn the color of the starch blue-black to find the rate of the equation. So that is what it really means in this question. So as soon as the thiosulfate is used up, the iodine that is further produced reacts with starch present and results in a color change. Okay, the time taken for this color change is noted, and and the reciprocal of this time is used as a measure of the reaction rate. Okay, reaction rate. Okay, so give the color change, right? So as so initially it is colorless, and when this iodine surplus amount of iodine starts to react with starch, it turns into blue black. So colorless to blue black, right? So you basically have to plot a graph. So on the x-axis I have the volume of H2O2, and on the y-axis I have rate of reaction, right? So basically I have multiplied the rate of reaction value with 10 to the power minus 2. I did that to remove of this 10 to the power plus 2, right? To remove of this 10 to the power minus 2 in order to simplify up our values. This is what I've done over here. So 10 to the power minus 2 time rate and volume of hydrogen oxide, and I plot a graph, right? And this is a rate versus concentration graph, right? Rate versus volume graph. Okay, state with reaction with order with respect to hydrogen peroxide, the order of the reaction, right? So this is going to be a first order, because this is a positive graph with a constant gradient, right? The positive graph with a constant gradient. Order 1, this is because the gradient is constant, or positive graph with a constant gradient. The continuous method of monitoring the continuous monitoring method was used to investigate the kinetics reaction between magnesium and sulfuric acid at different temperature. Okay, the equation for this reaction is this and this. For 80 degrees Celsius, that, and the result shows the temperature for 80 degree. Calculate the rate at 15 seconds using tangent shown, right? So calculate the rate at 15 seconds. So at 15 seconds you're going to draw up this tangent, right? And what you're basically going to do is you're going to find the gradient of this tangent to find the rate. You find two suitable points from the graph, and you then do what is then find the rate of a reaction. So del y by del x is going to be, I have taken up 69 and 20 as my y values, and 30 and 3 as my x values. I mean, you can basically take up any values, but make sure that it covers at least 50% of your gradient, right? 50% above for your gradient. And I have received a value of 1.8 centimeter cube per second, because do not forget to write up the units, right? Because this thing delta y, the value for the unit for delta y axis is centimeter cube, and the unit for this x axis is going to be second, right? So centimeter cube per second. Let's just move on, right? So the temperature of the reaction was changed to 75 degrees Celsius. Draw a line on the graph to show possible effect, right? So temperature. So first of all, the investigation was being carried out at 80 degrees Celsius, right? And this was the graph for it. And once the temperature is reduced, the amount of product produced is going to be the same as well, but the time taken to produce the same amount of product would be greater, right? The time taken to produce the same amount of product would be greater, like 70 centimeter cube of hydrogen is going to be greater, because as temperature decreases, rate of reaction decreases as well, right? So yeah, this is what I've written over here. Same volume of H2 gas will be produced. However, the time taken to produce 75 centimeter cube of H2 gas with 75 degrees Celsius will be more than in 85 degrees Celsius. Sorry, that should be 80 degrees Celsius. 80 degrees Celsius. This is because as temperature decreases, rate of reaction decreases as well, right? So let's just move on to the next question. All right, this question is from energetics, basic one. Okay, many effervescent products such as vitamin tablets are solid which contain citric acid. Okay, and this is the formula, and sodium hydrogen carbonate. Only when these tablets are when the tablets are added to water is fizzing. Fizzing is observed, right? Fizzing is due to the carbon dioxide being produced. The equation for the reaction is shown. This react to form this. Give two reasons why this reaction is thermodynamically feasible. So let's just check the number of moles of the product: 336, 7, right? 7 and 314. So 4 moles of reactant produce 7 moles of product. Hence the disorder increases, and hence the rate of and hence Daylight system increases as well, and hence the Daylight total becomes greater than 0. As del S system increases, del S total also become greater than 0, and hence the reaction is feasible. And also I can see that from solid, gas is being formed, right? So hence from solid, as gas is being formed, the entropy increases as well, because I have said in my earlier section that entropy of gases is greater than the entropy of solids, right? So let's just oh yeah, and also yeah, let's just move on. 4 mole of reactants produces 7 mole of products, hence the LSC increases. This is because these are increases, and hence rate of reaction becomes thermodynamically feasible. Also, gases formed from solids, right? This describe in terms of particles involved why reaction does not occur until the tablets are dissolved in water, right? So basically, when the tablets are solid, they are in a crystalline structure. So suppose the ionic crystalline structure type of scenario, right? They are in a crystalline structure, and as a result they cannot move. However, when they're dissolved in water, this structure breaks down and ions are formed, and these ions can move, and hence reaction can take place. Clear? Basic IGCSE comment on why reaction takes place when ions are produced, right? This is what I have written. In solids, the particles are in lattice, hence particles are not able to collide and react, right? When dissolved in ions, when dissolved, ions form that can move and allow the reaction to take place, all right? So for the reaction at 25 degrees Celsius, the standard entropy change for surrounding is going to be this. Calculate the enthalpy change. Calculate the enthalpy change. So basically you have to find delta H, right? How do you find delta H from this one? So is surrounding enthalpy of is sur is gonna be minus delta H by T. Many students forget to give this minus sign, so yeah, please take that into account. You plug in into the delta surrounding value the temperature, but you have to convert the temperature into Kelvin, and from this thing you can make delta H the subject and find the value of delta H, and you have to include unit, that is kilojoule per. This is in joule per mole, right? So what you have to do is you can divide this by 1000 to convert it into kilojoule per mole, or you can leave it as joule per mole. I would suggest that converting it into kilojoule per mole. So yeah, this is what I've done over here. Let's just move on. The enthalpy change of solution, delta S solution of sodium hydrogen carbonate is this. Enthalpy change of solution is this. Sketch enthalpy level diagram to show the relationship between enthalpy change of solution of enthalpy change of solution, lattice energy, and enthalpies of hydration for dissolving, right? So before we do on this question, let me just clarify something. This delta solution is the enthalpy change when 1 mole of an ionic solid dissolves in enough solvent to form aqueous ions like Na plus aqueous plus Cl minus aqueous, NaCl solid, right? So this thing is what we refer to as enthalpy of solution, right? Enthalpy of hydrogen is, suppose we have gaseous ions, right? So Na plus, suppose gas, plus Cl minus gas, right? When you're converting this gaseous ion into aqueous ion, this is what we refer to as enthalpy of hydration, right? And lattice enthalpy is when we have this gaseous ion, right, and we are converting it into an ionic solid, 1 mole of a solid, right? This is what we refer to as lattice enthalpy, when 1 mole of a solid forms from its ions in gaseous state, right? And enthalpy of solution could either be endothermic or exothermic. So basically it depends, and whenever you're drawing up these enthalpy level diagrams, you have to make sure the direction of the arrow represent what value, either it is positive or negative, right? So whenever the arrow is going upward, this is going to be positive, and whenever the arrow is coming downward, it is going to be negative. And the positive arrow means the reaction is endothermic, and the negative means that the reaction is exothermic. And as I said that delta solution could either be exo or endo, right? So basically you first have to read the question and identify either it is endo or exo, but for our case they have made it easier for us as it is endothermic, right? So first of all, at the base you're going to have the solid, right? At the base you're going to have your solid, and at the top you are going to have your gaseous ions. So gaseous to solid, this is delta H lat, and from this solid to aqueous ion, this is going to be your delta H solution, and as it is endothermic reaction, this thing is going to be the arrow is going to be going upwards, right? And from gas to aqueous, this is going to be enthalpy of hydration, right? First you have to write this separately for sodium ions and for the cation and for the anion, okay, right? So all of these reactions are exothermic except for delta H solution, right? Because bonds are being formed. See, bonds are being formed, right? And as bonds form, and as bond forms, they are gonna release energy, and hence the reaction is gonna be exothermic. And when the bond breaks, it is gonna take in energy, and once it takes in energy, the reaction is gonna be what? Endothermic. Clear so far? All right, so let's just move on to the next question. Give me a moment, guys. All right. Oxalic acid has the IUPAC name of ethane dioic acid and has a molar mass of 90 gram per mole. Okay. The name oxalic acid is originated from the fact that it was first isolated from plants of the genus Oxalis. Some biologists they are just trying to frighten you up, so they're trying to piss you off. Do not worry on all this, because this isn't gonna be much difficult, right? Genus Oxalis, the formation of oxalic acid in plants involves the sorry guys, I'm having bad cold. Okay. The formation of oxalic acid in plants involves the hydrolysis of 2-oxo-butene-dioic acid, K, butene-dioic acid, dicarboxylic acid, okay, um, with water to form this and this ethane-dioic acid, okay. And the other thing, plants can form oxalic acid from glycolic acid, okay. Oxalic acid could be manufactured by oxidizing sucrose using nitric acid, blah blah, using presence of a vanadium catalyst, blah 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 blah. But basically, I'm not reading all of this because this seems to be unnecessary at this point. So let's just atom economy, right? So AMR, atom economy is AMR of desired products by all products, AMR of all products times 100, right? So the desired product from this reaction is going to be this one. So basically you have to find the AMR of this, and you know that the AMR of this is going to be 90. You just have to find the AMR of this, and that is going to be 60. Why? Because the AMR is going to be 60 for here, because we have a carbon over here that has 3 other hydrogen attached to it, and this is a carbon, oxygen, oxygen. So when you calculate all of this, you get a value of 60, right? So 60 plus 9, so 90 by 60 plus 90 is going to be times 100 is going to give you the atom economy of this reaction, okay. So give laboratory reagents required to convert glycolic acid to oxalic acid, right? Glycolic acid to oxalic acid. What I am seeing over here is that glycolic acid, give me a moment. Glycolic acid, this is a glycolic acid. So let's just draw a structure of this. CH2 COOOH, and here we have an OH, right? So we have to convert this thing into a dicarboxylic acid, right? Because this is we have one carboxylic acid, right? And we have an alcohol over here, right? We have to make this into an carboxylic acid. Anything clicks up in your mind? Because this is an alcohol and this is moreover a primary alcohol. We can make up a carboxylic acid from this using an oxidizing agent like K2Cr2O7, potassium dichromate 6, and dilute H2SO4, right? Plus heat under reflux, because we are converting an alcohol into carboxylic acid. So that's what I've written over here. K2 plus heat and dilute H2SO4 plus heat under reflux, right? Sucrose can be oxidized using concentrated nitric acid to form oxalic acid. Complete the equation, right? So this equation seems to be kind of tricky, but do not worry. So let's just find out the basic structure, basic ones. So how many carbon are over here? Because you cannot change over here, right? What you have to do is you have to change over here, right? So let's just basic math. Let's just take the math student in you. Let the math student in you, dictate over here. So you have 12 carbons, right? You have 12 carbons over here, and how many carbons do you have over here? You have 1 and 2. You have 2 carbons, right? So 6 times 2 is going to be 12, right? So yeah, the carbons are balanced, right? Now let's just balance the nitrogens, right? There are 36 nitrogens, right? So here we are going to have 36 nitrogen as well, right? Now hydrogen and oxygen is left, right? Now what you're going to do is you're going to subtract um, right? So you have this amount of night 36 times 2, 36 times 2, so this is gonna be 72 hydrogen, right? 72 hydrogen over here, sorry, 72 oxygen over here, and let's just calculate the oxygen over there. We have O4, right? O4 times 6, 4 times 6, 4 times 6, we have 24 over here. So 72 plus 24, we have a total of 96 oxygen, right? And let's just see how many oxygen we have over here. We have 11 and 36 times 3, 36 times 3, so 11 plus 36 times 3, we have 100. We have total of, we have a total of 119 oxygen, and but we have in this side of equation we have 96 oxygen already, right? So let's just see how many more oxygen do we need. 119 plus 96, so we need a surplus of 23 oxygen, right? So we have one oxygen over here, we are gonna add 23, so this thing multiplied by 23 gives us 23 oxygen. So this is how you find out the balance equation of this kind of questions. Clear? So let's just move on. If you do have any question in this one, make sure to comment below or reach me out directly. I will be more than glad to help you all. All right. Okay, give one observation, right? NO2 is formed, that is a brown gas. You have, by default you should know the color of nitrogen dioxide. Okay, a student, a solution of sodium hydroxide was titrated against 25 centimeter cube of oxalic acid. Okay, so in this beaker you have this oxalic acid, and using a burette you are just dropping and using burette you are just dropping sodium hydroxide, right? And the pH is increasing. Okay, both were in equal concentration, as the concentrations are equal, the volume are going to be the same as well, right? So I see that there are two equivalence point, which means that this is the diprotic acid, right? So as the concentrations are same, the first volume is going to be 25 for the equivalence point, and if the first volume is going to be 25, then the second volume for the equivalence point is going to be 50, right? So as it is double of the first one, and it is a weak diprotic acid, the pH is going to be equals to pKa. As it is a weak diprotic acid, the pH is going to be equals to pKa at half the equivalence point, half equivalence point, right? Half equivalence point for 25 by 2 is going to be 12.5, that is over here, and for 50, that is going to be 25 plus 50 divided by 2, that is 25 plus 50 divided by 2, 37.5, right? So 37.5 is over here, and this is going to be another equivalence point. Okay, select one indicator for each of the equivalence point, include the color at the end of the indicator. Okay, right? So basically over here you have to use your data booklet, and for this one the steep section is from 3 to 4.4, right? And methyl orange would be a good fit for this. And as the pH is increasing, this thing is gonna be orange, slightly orange, because methyl orange is orange, or methyl orange is red in acidic solution, and acidic, and methyl orange is red and yellow in alkaline, right? The yellow in alkaline, right? But this thing is between acidic and alkaline, right? Because the pH is increasing, right? Hence the color is gonna be in the middle of this red and yellow, that is gonna be orange, right? So let's just move on to the next question. Second indicator, right? The steep section is from 64 to 6.4 to 12 for 12.4. So basically you have to select an indicator, and I went with phenol red, right? And I have again selected the color of the phenol red that is in alkaline condition, because the pH is already higher as well, right? So I have went with orange as well. So let me just take a look at the data book. Yeah, red or orange, because it is not completely alkaline here, right? Because it is in the middle, right? So between yellow and red, it is going to be orange as well. So just why, if both indicators were present in the same time, why it would be difficult? Because as both indicators would be present, it would be difficult to identify, because the color of the mixtures would overlap, right? So determine the graph for 2 Ka values of oxalic acid using this. Okay, right? So what I said over here is that at half equivalence point, pH is going to be equals to pKa, right? So this is the half equivalence point, right? So the pH is going to be 1.3. 1.3 is going to be equals to pKa. pKa, right? And pKa means that log base 10 to the power Ka is going to be equals to 1.3, right? And from here take 10 over there and make Ka the subject, and repeat the same thing for 37.5, and you will get the value. That you need for Ka, right? So pH is pK, right? So whenever there's a prefix p, it means that minus log base 10 to the power h plus, right? So I feel like I made a mistake over there. That is, be minus log base 10 to the power Ka should be equals to pKa. So let's just move on over there. So yeah, that is what I have written over here, and that's how I find Ka here. So let's just move on. How many questions do you have? Okay, 3 more questions to go. Spinach in one plant source of oxalic acid. Spinach is one plant source of oxalic acid. Approximately 700 milligram of oxalic acid can be extracted from 100 milligram of spinach. From 100 milligram of this spinach, we can get 700 milligram of this acid. High performance liquid chromatography HPLC is used to analyze the extraction process. The HPLC equipment is connected to a detector which records the peak when substances passes through the HPLC column. Suggest how a pure sample of oxalic acid could be used to identify the oxalic acid peak in chromatogram of the spinach extract, right? So they both would have the same peak, they both would have the same retention time. So find the retention time of the pure sample of oxalic acid and then compare with the sample of the spinach, right? This retention time is the time taken for a sample of something to be detected once it is inside high performance liquid chromatography or gas liquid chromatography by the detector, right? So the time taken for the sample to be detected after being inserted is what we refer to as retention time, right? So 0.558 mole per dm cube solution of oxalic acid is used for cleaning. Calculate the mass of spinach required to make 500 centimeter cube of oxalic acid. Mass of oxalic acid. Okay, 500 centimeter cube of oxalic acid. You have to find the mass, right? So first of all, you have concentration and you have AMR, right? So basically, what you're gonna do is find out the moles first of all. So number of moles is going to be this concentration times this volume, right? And once you have the number of moles, what you could do is you can easily find the AMR, because now uh, number of moles is mass by AMR, right? And mass is going to be number of moles times AMR, and you have an AMR given to 90, right? Then you just use a unitary method, because from 100 gram of spinach you'd get 700 milligram, and from 1 gram of spinach you'll get how many milligram of acid, and then from the answer and from this mass that you calculated, how many mass of um, oxalic acid you're gonna get, right? So basic maths, basic unitary method maths. So here I have done with that. 25, I get 25.11 gram, right? So for this much of the acid I need 100 gram for spinach. For 1 gram I need this, and for this 25.11 gram of this acid, I need this much gram for spinach, right? Right, so let's just move on. Write in equation excess phosphorus with excess, okay, right? So this was a carboxylic acid, right? And PCl5, we use PCl5 to test for this what should I say, we test for this OH group, right? So PCl5 does what is, it removes the OH and Cl gets add on, and then we have some common stuff that you have to memorize. POCl3 plus HCl. So here that is what I have done. I have replaced this OH with 2Cl, and yeah, I get POCl3 plus HCl, and HCl gives a misty film, right? So basically you have to memorize this equation, right? So yeah, that was more or less about the paper, I guess. So yeah, if you did find the video to be helpful, then drop a like, comment, and subscribe. And yeah, if you do have any other questions, please feel free to ask me below. I'll be more than glad to help you all. Thank you all. Have a great day.